Prime numbers are the multiplicative building blocks of all whole numbers. Every composite number you can think of can be broken down into smaller, indestructible prime factors. The question we are exploring today is, do these building blocks ever run out? This chart shows the prime numbers distributed among the first 100 integers. As numbers get larger, primes become less frequent, and their spacing becomes highly unpredictable. We cannot simply look for a visual pattern to figure out if they eventually stop. This diagram outlines a mathematical strategy called proof by contradiction. To understand if the primes continue forever, we will temporarily accept a false reality. We will assume someone has handed us a complete, finite list containing every single prime number that exists. We have to do this because manually checking an infinite list of integers is impossible. By forcing a hypothetical n to our list of primes, we create a boundary that we can actually test mathematically. We will test our supposedly complete list using an engine designed by the Greek mathematician Euclid. We multiply every prime on our finite list together, and then we finish by adding exactly 1 to create a brand new number, which we will call n. Let's run a small test case. Suppose our complete universe of primes contains only 2, 3, and 5. Multiplying those together gives us 30. Adding 1 gives us our new number, 31. Now we look at the mechanical effect of that plus 1. If we divide 31 by 2, we get a remainder of 1. If we divide it by 3, we get a remainder of 1. Dividing by 5 also leaves a remainder of 1. Because division by any prime on our list leaves that extra remainder, we know 31 cannot be built by 2, 3, or 5. It is completely missing from our original list. Adding 1 to the product of any finite list guarantees a new number that structurally refuses to be divided by anything on that list. Let's expand our list to include 2, 3, 5, 7, 11, and 13. Running these through the engine generates the number 30,031. Before we move on, what happens when we divide 30,031 by 11? What is the remainder? Because of how we built it, the remainder is exactly 1. But here is the trap. 30,031 is a composite number. It can be factored into 59 multiplied by 509. When we compare these two new prime factors against our supposedly complete list, neither 59 nor 509 is there. They are new discoveries. The new number n does not have to be prime itself. If it is composite, its prime building blocks must be unlisted, because dividing by any of our listed primes will always leave a remainder. Euclid's engine doesn't guarantee a prime number directly, but it mathematically forces the existence of at least one new prime outside our complete list. The initial assumption defeats itself. The guarantee that we will never run out of primes is what powers modern digital security. Public key cryptography, like RSA, relies on our ability to endlessly find massive, novel prime numbers to secure data. This diagram brings us to the final step in our logic flowchart. We assumed the primes could be contained in a finite list, followed the consequences, and found a contradiction. The list was not complete. Because every attempted finite list can be used to generate a prime outside of itself, no finite list can contain all primes. There are infinitely many. To recap the proof, first, assume a finite list. Second, multiply them all and add 1. Third, recognize the new number has a prime factor missing from the list. Therefore, primes are infinite. Proving that an ending is impossible guarantees that the search can never finish. Every attempted boundary simply creates a new beginning.